Hello physics students. In the last video, we studied series and parallel circuits. Specifically, we learned how to determine the resistance, the current, and the voltage in any part of either circuit. But the College Board requires that we go a little bit further. It requires that you be able to calculate the ratios of currents and voltages in the two kinds of circuits. So that's what we're going to do in the first part of this video. The second part of the video, what we're going to do is we're going to learn how what ammeters and voltmeters are, and also how you can correctly hook them into a circuit to measure current and voltage in a real circuit. So let's begin with the first part, calculating these voltages. So the first thing we're going to do for parallel circuits, we're going to calculate the current ratios for the circuit, namely the current of the current in one of the resistors divided by the total current in the entire circuit. So to analyze this, we're going to just plug in what the two currents are according to Ohm's law. Remember, in parallel, everything gets the full voltage of the battery, every single resistor. So the current through resistor 1 is I equals V over R, 1. And for the current total, you can find the total current by using total voltage over total resistance, and you'll get the total current. Now, we've got a division of two fractions, so we could convert that to multiplication by flipping over this bottom fraction over and multiplying times the top fraction. You see that the voltages go away because the voltage is the same everywhere throughout a parallel circuit, leaving us the ratio equal to Req over R1. That's how much of the current goes through resistor 1. Now, I'm not exactly sure what they mean by this goal. Maybe this is far enough, but I've never seen such a question where they ask you to calculate something like this. I'm just going by what's published in the curriculum. So in case they want you to simplify this, I'll show you how you could simplify it a little bit. But again, this may not be necessary. So Req, I plug in what it is. It's the reciprocal rule, as we learned in the last video. Now, to the minus 1 means that this really belongs in the denominator. So I bring it to the denominator with R1. All that's left in the top is 1. And now I can simplify this by multiplying top and bottom by R1 times R2 times R3. And basically, I'm multiplying this fraction by 1, so I'm not changing anything. You see that the R1s will cancel and leave just R2 and R3 on the top. Now, if I distribute these three terms to all three of these fractions, you can see that in the first fraction, I have all three of these divided by R1, which just leaves R2 and R3 in the top here, right there. If I bring this term right here in place of the 1, because I'm distributing again, the R2 cancels, and that leaves me R1 and 3 in this term. And the same for this last term, the R3 will cancel, giving me R1 and R2. So here's an expression for the ratio of the total current, the current in resistor 1 over the total current. So for the ratio for resistor 1, you see that we have the product of all the resistors without R1 in there. And then in the bottom, we have like the sum of all the products of all the pairs of resistors. So if you wanted to do the same analysis for resistor 2, the bottom would look exactly the same, but instead of R2 here, we would have R1 times R3. And so that's how you can determine this ratio. Let me create a pause here to allow you to catch up if you need a moment to catch up. Okay, let's move on. What we're going to now calculate is not this ratio for a series circuit, because you'd get 1, right? Everything has the same current in series, so if you do I1 over I total, you're going to get like maybe 2 amps over 2 amps, you get 1. So that wouldn't really be meaningful, but the voltages are all different in series, so they require you to calculate the ratio of the voltage in one resistor over the total. Now, using Ohm's law, you can rearrange for V, and it equals IR. So V1 is I1R1. That's the voltage in resistor 1. And V total is I total R total. And you can see that since these have the same current all throughout a series, they cancel. And that leaves us this expression. Again, that may be far enough, but I don't know exactly what they mean by their objective there. So if you needed to, you could just plug in what R and Q is and maybe answer the question that way. So I'll give you a moment to catch up if you need to, copying the notes down. Okay, so that's the conclusion of part 1 of this video, calculating these ratios for series and parallel. The next thing we're going to do is we are going to learn, or you're going to learn, what a ammeter is, what a voltmeter is, what they achieve, and then also a little bit how to use them. So first thing, we've used these before in some of our experiments when we were measuring equipotential surfaces. We used this as a voltmeter, so we called it a voltmeter back then, but it's actually called a multimeter. Why is it called a multimeter? Well, because it measures multiple things. So here's a closer view of the multimeter, and you can see that there's a dial here. It's on off right now, but I could turn it like this, like we did in the experiments I just talked about, and now this multimeter becomes a voltmeter. This measures direct current, like the voltage in batteries. If you wanted to measure the voltage out of your wall outlets, that oscillates. So you turn it here. It's still a voltmeter, but for what we call alternating current. It should read 0 for some reason. I don't know why it's reading 0.5 volts. And then if I turn here, I'm measuring ohms or resistance. So now this is an ohm meter. And if I turn like this, it's now an ammeter because it's measuring amps. Okay, so this just measures different kinds of amps, different levels, and this is for alternating current amps over here with the little squiggly lines. So this is what we're going to use in the demonstration. It's also what we're going to be using in our future circuit experiments. So what I'm going to do now is reconfigure the camera to show you the most basic circuit we can make with a battery, the light bulb, and some wires again. And then I'm going to show you how I can use meters like this to measure the current in the circuit and the voltage at any part in the circuit. So give me a moment, I'll reconfigure the camera. So what I have here are the basic ingredients of a real simple circuit. I've got a voltage source, these batteries making a voltage of 4.5 volts, a bulb, and some wire. The wires I just coiled up so that it's a little easier to see and we don't have a big dizzying array of wires that get us all confused. So what I want to first say is something that maybe you're getting sick of hearing me say it, and I hope you are, because maybe that means that you're really remembering it. Voltage, this 4.5 volts, is not this wire, it's not that wire, it's 2 wires. It's always between 2 points. So 4.5 volts is both of these, okay, from one to the other. So in order to get this circuit to go, I've got to connect it to both sides. So I go like this, and the bulb turns on. The electricity is flowing around. So because of that nature of having to have both sides of the voltage, a circuit must be a loop, like a circle almost in a sense. And if I interrupt anywhere, the circuit goes out. A lot of people in everyday world would say, okay, if I disconnect from the positive, the circuit surely goes out because I don't have the positive anymore. But the negative side, if I disconnect there, it goes out. Or anywhere in between. If I interrupt that loop at any point in the circle, it goes out. So now what I want to do is measure the current in that circuit. So I'm going to take this multimeter and turn it to measure amps. In other words, I'll turn it into an ammeter by turning it to this point, 20 amps. It's reading 0, obviously, because the current's just sort of flowing past the meter. In order to measure the current, what I have to do is first open up the circuit and then connect the wires, complete the connection with the ammeter. So the important thing about the ammeter is that it must go in series with the circuit. See how this is in series? It's all one chain. You put an ammeter in parallel, not only is it not the way it's supposed to work, and it won't work, but you could create damage, and I'll explain why later in this video. It must be within the loop. I could have put the ammeter here before the bulb, after the bulb. It doesn't matter because I in a series circuit is the same everywhere. So we see 0.39 amps being produced. So it's, in a sense, it's like a toll booth for the electrons. And, you know, toll booths, you have to drive through them to be charged a toll. So it's this here, the electrons driving through, and then the toll registers here. But what we want to do is we want to make an ammeter such that it doesn't restrict the current. Because if there was a high resistance here, without it, the bulb would be nice and bright. But if this had like 1,000 ohms and then I go like this, suddenly the REQ of this circuit would increase, more resistance, less current, and the bulb would be dimmer. I would be changing the circuit if this had a high resistance. So they're designed to have as low a resistance as possible. Hopefully you want zero, but of course nothing is zero resistance, so you try and get it as low as possible. So that's an ammeter hooked correctly into a circuit. Let's now summarize everything that we observed in the demonstration. Okay, so maybe what I'll do is I'll create a pause to allow you to copy these down first, and then we'll go over them. All right, so the ammeter, first of all, it's the symbol we use in a circuit. Remember, in circuits we often use, or we always use symbols for things like resistors. That means resistor. Well, in ammeter we use this symbol in a circuit. A circle with an A inside of it with two lines like this. And what it does, obviously, it measures current in a circuit. It has low resistance. Usually, as a practical matter, well, first of all, we want it to be 0 ohms so it doesn't distort the circuit, as I mentioned. But no matter what you do, you can never eliminate resistance unless you're dealing with superconducting materials. So there is always some kind of small resistance to an ammeter. Maybe it's like 1/2 of an ohm or something like that. And it must be connected in series in a circuit, never in parallel. If you connect the ammeter in parallel, it's possible to damage either the circuit or the meter or both. So you never want to put it in parallel with anything in a circuit, because basically, as I said, it acts like a high-speed toll booth in a highway. So like if you have the toll booth in series with the roadway. In other words, the road has to pass through the toll booth in order for it to work. If you put it off to the side and the cars just go past it, then you know, you either don't register the circuit, or if they go through, they could cause an overload. So that's the ammeter. Now what I'm going to do is I'm going to show you the circuit again, and I'm going to show you how you could use a voltmeter, this multimeter turned to measure volts, to measure voltages in a circuit. So let me reconfigure the camera. So here I have the circuit that I set up earlier with the battery, the bulb, and the ammeter connected correctly in series to measure the current in the bulb and actually in the battery also. Now suppose that I wanted to measure the voltage in this circuit. Maybe the voltage at the light bulb or the voltage of the batteries. So what I need is another meter. And notice that it looks exactly the same as the first meter. And that's because it is the same. These are called multimeters. So turning the dial, as I said, just means that you configure it in a different way to do a different thing. This is an ammeter, this is a voltmeter now. So again, remember, voltage is always between 2 points. So now when I take these voltmeter probes, if I want the voltage of the light bulb, what I need to do is measure, not like this, but from one side of the bulb to the other. And that means touching this here and the other wire on the other side of the bulb, and you see that you get a reading, looks like about 3.6 volts of the light bulb. So notice now that since it's from one side of the bulb to the other, is actually connected in parallel to the light bulb, right? So it's not in series, it's not within the original chain. It's like off to the side in parallel with the bulb, and that's how you use the voltmeter, okay? If I wanted the voltage of the batteries, I could go here in parallel to the batteries, and I get the same thing, approximately 3.7 volts. So since it's in parallel, what that means is that the resistance here had to be low because it was in series. Here, since it's in parallel, we don't want any of the current to skip the light bulb and go through the voltmeter instead. That would change the circuit. We want it all to still go through the bulb and none to go this way, which means that the voltmeter now has to be built in such a way that it has a very high resistance. Ideally, you would want an infinite resistance. No such thing, though. So a typical voltmeter like this might be like 10 million ohms. So a little tiny bit of the current goes out and bypasses the bulb, but you try and minimize it as much as possible. So that's how you use a voltmeter shown on a real circuit. Let's go back to the board and I'll summarize what we saw here. I just thought of something else that I want to show you regarding measuring voltage with the voltmeter that I find very interesting. So this, remember, voltmeters have a very high resistance of the magnitude in the millions of ohms, which means that it's perfectly safe to stick, well, I shouldn't say perfectly, because you still need to know what you're doing, but it's safe to stick these prongs into the outlet and measure the voltage. First, though, I have to configure the voltmeter properly. I turn it to 200 V with a squiggly line. That means it's going to be measuring alternating current, oscillating current like the outlets in the wall, and it can measure anything up to 200 volts. So then what I'm going to do is stick in here. Now, first I want to explain what all three of these connectors are. The smaller connector, the smaller prong is what we call, electricians call the hot terminal, the hot wire. And that means it's the one that has the voltage going to it, the oscillating voltage. This is called neutral and this is called ground. Both of these are literally connected to the ground, planet Earth. If your house is wired properly, you can go outside where the service comes in and look for a spike, a copper spike that's driven into the ground to ground your house and ground this prong and this, by the way. So these are 0 volts at all times connected to planet Earth. So in theory, it's possible to stick a paper clip in both of these, holding it with my finger, this one right here, that one, and that one. Of course, you don't want to do that because electricians do make mistakes too, and sometimes they wire this incorrectly. And so you don't want to find out your electrician that wired your house made a mistake by getting electrocuted. So it's never a good idea to test electricity with your body parts, right? So you want to use something like this, a voltmeter. So now that I have it configured correctly, I'm going to stick the two prongs into these two outlets to measure the voltage difference between the two, the hot and the neutral. So there I go. I've got them in there, as you can see, and it's somewhere around 120, which is the standard in the United States for the voltage of an outlet. In Europe, of course, you may have heard it's 220. They have a higher operating voltage. So I'll take these out now. So that's the voltage between those two prongs. But I could also measure the voltage between ground and that hot. Maybe I'll go like this from this side to maintain a good connection. And the hot, and I should get 120 also. Oops. I got to find the right connection in there because the prong size is not correct, but where is it? There it is. So 120 between the ground and the hot. Now, the voltage between the neutral and the ground is 0 because they're both connected to the earth, so there's no voltage difference. So interesting how you can use a voltmeter to even measure the voltage of an outlet at home. Okay, let me summarize what we saw in the demonstration. Okay, so here are all the points. Let me create a pause to allow you to copy this down before I talk about them. Okay, so voltmeter, the symbol for that in a circuit, when you see a circle with a V in it and two lines coming out like that representing the probes, the probe wires, right? So as we saw, you know, the meter has these two wires coming out of it. So these are like the wires that come out of the meter that you touch to various parts of the circuit. What it does is it measures voltage or potential in a circuit. And of course, what we mean by that is always from one side of something to the other, because voltage is always 2 points. It's the work per charge along a path or the electric field integrated along a path. So it's always between 2 points you got to touch. And the voltmeter has a high resistance, something of the order of 10 million ohms. That's what a typical, probably like a voltmeter like this has. Ideally, we want it to be infinite ohms, but it doesn't, you know, achieve that. But that's what you ideally want, but a real high resistance. And then it must be connected in parallel in a circuit. And I didn't underline the word must because it's not like you're going to, it's not like so imperative here where this can never go in parallel. This, and it must be in series. If you put a voltmeter in series with a circuit, it doesn't damage anything, but it distorts the way the circuit behaves. So, you know, it basically ruins the experiment, but it's not going to ruin the meter or the power supply. And basically what it does is it acts like a tire pressure sensor, okay? So that's the voltmeter, that's the ammeter. What I'm going to do now is sketch a few diagrams to show you examples of how you can correctly plug in ammeters and voltmeters into a circuit to make the appropriate measurements, and also examples of how you can do it incorrectly. So hopefully you'll be clear about how to connect these together. Okay, so here's the circuit, and it's just basically a voltage source and a resistor, kind of like what we saw on the desk over here, with this being the light bulb instead. So what I do is I put the ammeter within the loop right here. This is the circuit loop between the battery and the resistor. So it's like the toll booth. As the charge is passing through on the way to the resistor, it records the rate at which it flows. The voltage sensors can go on either side of the battery. They can go here measuring the voltage of the battery, which is the voltage of the resistor, or you could put it right on either side of the resistor. Either one is correct, okay? So there's one example. The next example that I'm going to do is, so notice I put yes here. That means that's correct. No, this is going to show an incorrect setup. Okay, so let me create a pause, allow you to copy this down, and maybe this if you didn't catch up before, and then I'll explain what's wrong over here. Okay, so the problem with this, first of all, the voltmeter stops the current. It's like 10 million ohms right here, so very little current in this circuit. Without it, there'd be more current. So this blocks the current, it distorts the circuit, it didn't damage anything. This, however, does damage the circuit. Now, you may not realize this, but this ammeter and this resistor are actually in parallel. If I put the ammeter here, for example, if I put a resistor here, everyone would say, oh, that's parallel, right? Well, if I move the resistor on this side, I still have the electricity coming out of the battery and dividing and splitting up and then going through the two and then joining together. So even though it's here, it's in parallel. Even though it looks a little different, it's still the same exact as if I put the ammeter here. And so what I have here is a branch of electricity where I've got a voltage, the full volts of the battery to the ammeter, which ideally has 0 ohms. So when I do, maybe this is like a 12-volt battery, divided by 0 ohms, I get an infinite current right here, or a very large current, which will spike up, damage either this or that, or both of them. So this is what we call a short circuit. That's the word where you create a path with a very little resistance for voltage, and this current spikes up, and you can have damage, or even in a house, if this were in a home, you could have a fire, an electrical fire. So short circuit, very bad thing. All right, so now what I'm going to do is I'm going to do a combination circuit, which we haven't studied yet for resistors. So I'm jumping a little bit ahead, but I'm going to show you where I could put all kinds of meters all throughout a simple combination circuit, and then we'll talk about what's correct and what's not correct. So here's a basic circuit. It's a combination like we studied with capacitors. I've got a parallel circuit, and then I've got another resistor over here which is in series with that. And we're going to talk about analyzing that more later. But you could kind of see the logic of this circuit, that the electricity is going to go all through R1, and then it's going to split here and go through some in R2, some in R3, join again, and return into the battery. That's the loop. So now what I'm going to do is I'm going to insert a bunch of ammeters and voltmeters, and then I'm going to explain which ones are correct and which ones are wrong. So let me do that now. Okay, so let me create a pause to allow you to copy all this down, and then I'm going to talk about it. All right, so I inserted a voltmeter here in parallel with R1, and then an ammeter after R1. Then I put an ammeter down in this branch with R2 and a voltmeter off to the side of R2, and then I put an ammeter on to R3 on the side like this. So everything is correct except for this here. For example, voltmeter A, notice it's in parallel with R1. So it's basically like me taking this, of course everything has to tangle up. Okay, so taking these two leads, and here's my voltmeter, and I connect to either side like this and get the reading on the voltmeter across R1, so I call it V1. Then the current goes through R1, none goes around here because this is so high a resistance, and it must pass through ammeter A. So that correctly measures the current that came out of R1. In other words, the current in R1. But notice it's also the total current, because basically the battery sent the total current this way all through R1. So this also measures I total in addition to I1. And then notice that that current then will split here, some down to R2, some over to R3. So it also measures the combined currents of these two resistors. Just a minute, I'll be done in a minute, okay? Okay, so, and then ammeter B, right here, it correctly measures only the current in resistor 2. Notice that right here, any current destined for resistor 3 never goes through that toll booth, only the one destined for R2. So it only measures current in this branch right here. And voltmeter B also measures the voltage in resistor 2 correctly, because again, it's like I take these two prongs and I touch them to either side here, and I get the voltage of only resistor 2, okay? And then finally, ammeter C, as I said, is incorrect because it's in parallel with this resistor. So it shorts resistor 3. In other words, the electricity, rather than going through a resistor, it goes here where there's, in theory, ideally no resistance. So it all goes through here, bypassing that resistor. Now, I just wanted to point out that that, by the way, doesn't cause any damage. And the reason why in this particular case it doesn't actually damage anything is because there's still a resistor within the loop, R1. The current must go through R1 to get to the ammeter. So yes, the ammeter causes the current to bypass not only this resistor, but this resistor, but there's still some resistance in the circuit. So it completely changes the circuit to behave in a way that is no longer like the original. By the addition of that meter, it changes all the current values, but no damage occurs. So that's a little bit about how ammeters and voltmeters work, a little bit about how to connect them in a circuit the correct way. Make sure you understand all the ways that they need to be connected, series versus parallel. And also, don't forget that first analysis we did where we calculated the ratios of the volts for a series circuit and the ratio of the currents in a parallel circuit. All right, I hope you enjoyed the physics video, the demonstrations, and the ideas and concepts. I'll see you in the next physics video.